Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is Adi, your lecturer for statics course. And in this recording, we'll discuss, it will be a lecture on chapter 10, mode of inertia. All right. So previously we have learned about chapter 1 to chapter 5, and then we skipped chapter 6 for a while. We went straight to chapter 9, which was, what was that? Centroid, right? And then we go to chapter 10, which is mode of inertia. Okay, if you realize the name itself, there are two keywords. One is moment, and another one is inertia. About moment, you have learned about moment in chapter 4, right? And then this inertia you have learned in physics. I don't know when you first learn about inertia. So we'll discuss on the concept of moment of inertia in a while, right? In this chapter 10, there are 4 subtopics. First one is about the definition of moment of inertia for areas, right? Moment of inertia, we denote this as I, right? And then we say I, X, or I, Y, something like that. X is axis, Y is, we will discuss about that, right? Then we'll go to number 2, which is parallel axis theorem for an area. Basically, it means that basically you want to find moment of inertia of an area, right? Which the centroid is not at the axis that you want to find about the moment of inertia. Okay. And then the third one, we'll move to rays of gyration, right? Of an area. So there is a concept. I mean, of course, there is a formula, and if you understand number 1 and number 2, I mean, this rays of gyration, the formula will be simple for you to understand and use. But there is a concept, the real concept behind rays of gyration. What rates of gyration? Why you have to learn about this, right? And then number 4, which I personally believe the most important thing, is about moment of inertia for composite areas. The reason is because lots of things in reality, in practical terms, they are composite areas. And composite areas, you have seen the types of composite areas in last chapter, right? In chapter 9, you learn about, for instance, this shape, and this shape. For instance, a beam like this, it has a cross section, right? Like this. This is a beam, right? Which has a eye shape cross section like this, right? Or we call it wide flange beam. Okay. So you can divide into first shape number 1, shape number 2, and shape number 3, isn't it? You remember about that? So it will be the same concept here. But in the previous composite areas, we learned about how to find the centroid, right? Now here you will find out how to find the moment of inertia if you have this kind of composite areas, right? The areas means that, again, kind of complicated areas, or not really complicated, but certain types of area, cross-section area like this, right? Where actually you can divide into simpler shape or known shapes like rectangle or triangle or circle or semicircle, right? You remember the whole example on, you have a hole in the YouTube video, right? Okay. So next, okay, this is the first one, definition of moment of inertia. Okay, moment of inertia is I. You use I. Okay. So moment of inertia, it measures objects' resistance to change in rotation or capacity of cross-section, right, to resist bending, right? And you have to specify this with respect to axis of rotation. You rest about, there is a I mean, these words coming again and again: rotation, bending, rotation, right? So that's why we talk about this moment of inertia. Moment, what happened to an object when you apply moment on it? In chapter 4, we'll have rotation, right? You apply moment, remember this, clockwise or counterclockwise rotation. So when you apply moment, you have rotation. right? So mode of inertia basically is the ability, in general term, I mean to make it simple, is an ability for an area or cross section, okay, area or cross section to resist the rotation or to resist the bending, right? In fact, if you go to advanced course like mechanics of materials or structural mechanics, for instance, so you will use this mode of inertia when you discuss this kind of things, bending, transverse shear, rotation, right? When you have this rotation, then you have mode of inertia, okay? Because when you have rotation, it must have a resistance, right? The resistance is moment of inertia, right? Of course, in this chapter, mostly you just have to calculate, right? But I hope you understand and you know what will be the next practical example or practical reason why you learn moment of inertia, right? And you can check this statement and try to understand, right? Okay, and also this statement, right? All these actually is kind of example on how you can understand moment of inertia. But generally speaking, like I said, simply said, the ability of a cross section or an area to resist rotation. As simple as that. Rotation mainly due to the moment. Okay, and for instance, okay, you have this RS beam, right? This RS beam. This is a beam. You apply load P somewhere on the beam, and one beam at R at the left end it is supported, pin supported, right? And at S it is roller supported, right? So there's this is kind of a case study. The same beam with different cross section. This is the first cross section, I shape. This is the second cross section, which is a rectangle, but you have the base is 30, the height is 300, right? And this is the third one, C, okay? C is the third one, which is 100 by 30 millimeter. The, the thing is here, if you realize, if you calculate, all of these, they have similar total areas, okay? The total area is not 300, is 3,000 millimeter square in all cases. All right, all of them. But the thing is, though they have the same areas, these three, A, B, and C, 1 and 2 and 3, right? And even if they are made from the same material, right? What will happen to this beam? Will they deform the same way or not? You understand that you apply the load, the beam will kind of deform like that. But how much will it deform this beam? How much? So actually, even if you have the same areas, total areas, like in these three cross sections, the answer is actually you won't have the same deflection. You don't have the same deflection. Okay, with the same material, the same total areas, with the same load, with the same loading conditions, with the same support conditions, you won't have the same deflection. Why? Because they have different shapes, right? And different shapes here will give you different moment of inertia, which means that this I and this I and this I, they are not the same. Because they are not the same, the calculation for stress and deflection of this beam won't be the same. Okay, you can even use simple example. Take your ruler, for instance, your ruler, you try to bend with different cross section. You understand what I mean? Try your ruler, you can try this B and C. Okay, try to bend it. You will find that if you try to bend it uh, in B, it will be even harder to bend it by C, right? Try to do it. Okay, do actually that it is the same, right? It is the same ruler, but why B will have you have it will be more difficult to bend cross section B? This is because of different moment of inertia. Okay. Okay. Just a quick note. The thing is that here, what happens is that moment of inertia of this A, number one, is I, right? It will be the biggest. This one will be in the middle, slightly smaller, and then this one will be smallest, right? The C. So because this is the biggest, the I shape here, you will have, because the highest I, this is the highest I, right? So you will have least stress and deflection. I mean, this kind of shape, cross section shape, will have less deflection. Will be more difficult to bend. As simple as that. All right. Okay. Now we go to the mathematical concept. So if you have this area, you see the blue area, and you define the x, y axis, right? Check the x and y axis. All right. And this is the origin, and this is the area A, the blue shaded area. And then if you want to find the moment of inertia of this area, right? And you have to understand, when you want to find the moment of inertia about this area, about any area, you have to find the moment of inertia about an axis. All right, so you have to choose whether it is Ix. Okay, Ix. I mean, if Ix means that it is with respect to x axis, or Iy. Okay, with respect to y axis. So mathematically, what you have to do is you have to take differential area dA, right? Take differential area dA like this. And then the differential at this differential area is given by this formula. If you take dix, no, sorry, dA is differential area. But if you take the moment of inertia of this differential area with respect to x, so will be given by differential of moment of inertia with respect to x equals to y squared. What is y? Y is the distance, programmed distance from x-axis to this dA, right? Y squared dA, and dA is the differential area itself, differential area, which means dx times dy, right? Same goes to diy. If you want to find moment of inertia, differential moment of inertia, di with respect to y, so this diy, right? So it is equals to, it is equals to x squared. X is this length, right? This is x, right? X squared times dA. dA is dx dy, right? And you have another one, dj node, okay? And this is equals to r, which is the radius, right? Radius squared dA. And this j, we call it as a polar moment of inertia, all right? That's why it is related to the radius, right? Polar moment of inertia, about the pole O or the C axis. Okay, so if what happens if you integrate them, integrate these three, so you will end up for Ix, this is the formula, integration over the area, y squared dA. For Iy, will be this formula, integration over area, x squared dA. And for J, polar moment of inertia, will be integration over the area, r squared, r is the radius, r squared dA. And if you substitute this r squared will be x squared plus y squared, and it will be Ix plus Iy. All right. Okay, so polar moment of inertia basically will be what? It will be Ix plus Iy. Okay, so this moment of inertia, okay, it is referred also as the second moment of an area. And the unit, what is the unit? Unit is length to the power of 4. Okay, meter power of 4, or inch power of 4, or millimeter power of 4, I mean, doesn't matter. But the thing is that it is length to the power of 4. Okay, to the fourth power, right? Uh, so this is the procedure to evaluate the mode of inertia for areas, right? First, you have to choose the differential element, this dA. Okay, differential element. So for instance, you have this area. Can you see that? This curve is defined by y equals to fx, right? And then it is bounded by this curve and x and y axis, right? So the thing is, you have to choose the differential element dA. Here, if you want to use this direct integration method, okay, this one in this 10.1, if you want to find Ix, which is moment of inertia about x-axis, like this, right? You will have to choose differential element which is parallel to x-axis, which means something like this. Understand that? You remember in chapter 9, we also chose our differential element, chapter 9, for finding the centroid and center of mass, center, all those stuff, right? But in chapter 9, you can choose any element. I mean, any element parallel to any axis, x or y, doesn't matter. It's just as long as you do it correctly, the rest of the steps correctly, then it will be fine. But in 10.1, okay, to find Ix, which means that you want to finish up about x-axis, this x-axis, right? You have to choose differential element which is parallel to x-axis, right? Same goes to when you want to find Iy, okay? So you have to choose vertical element which is parallel to y-axis, right? Can you choose, for instance, can you choose here, the first one, can you want to find Iy, but you want to choose vertical axis. Can you do that? The answer is yes, actually you can do that, but you have to go to 10.2, right? If you don't want to use, I mean, in 10.1 we'll discuss, our discussion will be on this, which means that you have the uh, differential element which is parallel to axis that you want to find moment of inertia about, right? And then for Ix, you can then only then you use this formula, integration over area y squared dA. And for Iy, you use this formula, integration over the area x squared dA. What is x? What is y? What is this y and a x? So it depends on the function here. Okay, y equals to fx, right? Okay, so this is the first example instance. Let me see. Yeah. This is the first example. Fundamental 10.1. The question asks you to find moment of inertia I, right, of the shaded area about x-axis. So is it Ix or Iy? It is Ix, isn't it? Okay. So this area, this area is bounded by, is defined by y cubic equals to x squared, right? And then it's bounded by this x equal to 1 and x-axis, isn't it? This is x equals to 1. Remember your calculus or your math, I don't know which one, and x-axis, right? So you have to choose your differential element, dA. Remember that one? Just we discussed about differential element, dA. So here, what do you want? Which one do you want to choose? This one, horizontal or vertical? It is horizontal, right? Why? Because you want to use direct integration, so you have to choose differential element which is parallel to the axis that you want to find about, the motion that you want to find about, because it is Ix about x-axis, so you have to choose differential element which is parallel to x-axis. And then this is the xy, right? Remember that one? Xy. And then how much is this? This length. This length is 1 minus x, isn't it? Total length is 1, and then this is x. This is x, right? So 1 minus x. And how much is this? This is what we call as dy, right? Differential of y. Okay. So this is the one that I said. Okay. So you have this differential element, right? And then you can define your differential element dA as what? 1 minus x, right? This length, and times dy. Okay. This. And then this x you can substitute from this equation, right? You can express x equals to y to the power of 3 over 2, isn't it? So you put here the x as y power of 3 over 2, and then you integrate Ix this equation. You express this equation because what you want to find? You want to find moment of inertia about x-axis, right? So Ix is given by this formula, integration over the area y squared dA, and you plug in this parameters. Y is y, okay, y squared. How about the ADA is 1 minus y power of 3 over 2 and dy. The boundary will be from where to where? From 0 to 1, right? Why? Because from here to here, right? From 0 to 1. Because this differential of y-axis of y. So it is y from 0 to y equals to 1, right? Then you do the rest and then you will get this answer, right? Ix. Okay, we go to second one. If you realize actually this is the same equation, right? Even the same diagram. It's just previously it was this area, right? Now we go the other way, the other area, right? Okay, so the question same, wants to find ask you to find Ix, which is the mode of inertia about the x-axis, right? So which one you want to choose? This differential element or this differential element? Which one? It is this one, right? Because you again want to do direct integration in 10.1. So you have to choose a differential element which is parallel to the axis that you want to find moment of inertia about, which is in this case x-axis, right? So you take this point, right? And then you draw the differential element, right? And then you define those lengths. The dy here, this will be dy, right? But now, probably we have to do this. Okay. How about this length? The horizontal length of this differential element. It will be how much? It is x, right? Previously it was 1 minus x, isn't it? Now it is x because it's from here, x equals 0 to x, so x, right? So, okay, this is what we just discussed. And we define the differential element dA as x times dy, right? So x is what? X is, again, we manipulate this equation of the curve. So you express x in terms of y, okay, and then you put here, and then you integrate this moment of inertia about x, which is Ix equals to integration over the area y squared dA. The rest will be the same, right? Okay. Okay. The third one, now we do the moment of inertia about what exists. So it will be the same procedure mainly, but now this one will be parallel with the what exists, which is something like this. So okay. Okay. Then you define this length. And this length, of course, this is the x, but the vertical line will be how much? It will be y, isn't it? Like this. And then you do this I, of course, sorry, you do this one first, the A, and then you express the A, and then you express IY, which is integration over the area, x squared dA, right? And then you integrate, you get the answer. Okay. And again, this one, and for want to finish about what exists, okay, take the point, take the differential element, right, which is parallel to what exists, right, which is vertical, and you define the length of this differential element. How much is the vertical one? It is, okay, this one first. How much is this? This is the x, right? How much is the vertical one? Vertical it will be, this is y, isn't it? Total is 1, so this is 1 minus y, right? So you have this. And then again, you do the differential element, express this differential element, right? And then you integrate with respect to area, okay, Iy equals to integration over the area, x squared dA. You plug in the values, you put the boundaries, you do the math, and then you get this mode of inertia about y axis Iy, right? Okay, this is all for 10.1. Next, we go to 10.2, which is the parallel axis theorem for an area. Okay, so the idea here is you have this area, right? You have this area, and you have this XY axis, right? And for this area, actually, you know where is the centroid, which is here. Okay, here you know this is the centroid. Can you see the centroid? See the point here. So here at the centroid, we define your x prime and y prime axis, which x prime axis is parallel to x axis, and y prime axis it is parallel to y axis. Is it okay? All right. So here, when you want to find this differential element, okay, one of inertia of differential element here, this one, this area, if you do about x prime and y prime, then that's fine, isn't it? But now what happens if you want to find the I x and I y, right? So this is the issue actually, right? So the parallel axis theorem here actually what happened is that if you want to find in this case in this area, if you want to find I x prime and I y prime, you just have to find this mode of inertia with respect to x and with respect to y, okay, about the centroid, because you know the centroid of uh, this area, right? But what happened if after you found this? What happened after that? You want to find the moment of inertia about x and y axis, which is the real x and y axis, okay? The other axis. That's the thing. This is for one axis, which is its own centroidal axis, okay? But now you want to find moment of inertia Ix and Iy, which is at different axes. Okay, so this is why you learn here, this one, 10.2, about the parallel axis theorem, right? So here some definitions, all right? You have the centroid C in this figure, yeah, in this figure, and you have this differential area dA, right? The location of this differential area from the x prime and y prime, again x prime and y prime are the x axis and y axis of this centroid, right? Or we call it centroid axis. And you have x and y, another axis, x and y, the real axis, right? And you define this as the y from x axis, okay, this y from x axis to the centroid, and the x from y axis to the centroid. All right, and then from the centroid to the A, you define this as y prime. Okay, the location of the A. Y prime is the vertical distance from the A to x prime axis, and this x prime, which is horizontal distance from the A to y prime axis, right? So for this, if you want to find moment of inertia of dA, right, about the x-axis, this x-axis, okay, not about the x prime. X prime axis is its own axis, its own centroid axis. Not about that. It's about the x-axis itself. So you have to define it as this, which is, what is this? Differential of the differential of I x versus the axis equals to y prime. Okay, this distance from the A to x prime axis plus dy squared dA. Is it logical? It's logical, isn't it? The total distance y prime plus dy, right? And you squared that one with times with the differential area. It's okay. But that one is for the differential moment of inertia with respect to x. That's why we call it dix, right? So to get the entire for the entire area, you want to find ix for the entire area, right? So you do integration, right? You integrate, so the left hand side will be ix, which is the one that you want to find, right? The moment of inertia of x axis, and then you integrate, it will become this expression, right? And if you realize in the bracket here, the square bracket, if you expand, you will have three terms. One is y prime squared. Second one is 2 dy y prime, right? And the third one is dy squared. Can you see this? The first term, second term, and the third term. This first term, you have seen this before, which was in 10.1, right? The first integral here, integration over the area of y prime squared dA is in 10.1, which is the moment of inertia of the area above the centroidal axis. Okay, this is what I say. If you do integration y squared dA, y prime squared in this case, you will get just this moment of inertia about its own centroidal axis, right? Not the other axis. Okay, but here in this question, actually, the question asks you to find the moment of inertia about the at the axis, which is x, not its own axis, right? So we go to the second one. So the second integral it is 0 because this y prime here, you substitute into y bar is 0 because the x prime, your x prime axis, this x prime axis, it passes through the centroid, right? So there is no distance, right? And the third one, the integral, okay, this third integral, right? It is the total area times the square of the distance. Okay, integration dA times the perpendicular distance dy squared. Okay, hence there is no second term, right? So you just have first and third term. So your ix now it is expressed as ix prime plus a dy squared. What is ix prime? Ix prime is the moment of inertia about its own x central axis. Is it okay? And then what is a? A is total area, and what is dy squared? Squared is squared, but what is dy? Dy is the distance from its centroid, right, to the from its centroid to the x-axis. Okay, you want to find moment of inertia about the x-axis. Okay. So similarly, if you want to find moment of inertia about y-axis, then you do I y prime, okay, plus a dx squared, right? And if you want to find polar moment of inertia, right, so it will be jc plus a d squared, right? Okay. Okay, this is 10.2, right? And then we go to 10.3, this radius of gyration of an area, right? 10.3. We'll discuss some examples later on 10.2, right? So we go to 10.3 first. Okay. Okay, consider this. You have this x and y axis, right? X and y axis. And you have this area, okay, this A area, right? And you know the distance from this x-axis to this kind of the centroid, right? Perpendicular distance, right? So in this case, actually, because we have learned in 10.1 and 10.2, you know how to find ix, right? In this case, same goes here. You know how to find iy, right? Even in both cases, you can find ix and iy. But I want to focus on the first one for ix and the second one for iy, right? So here, what happened is this ix, you can express this ix as this, which is the perpendicular distance squared times the a, right? And you can manipulate this, which means that you can express this perpendicular distance kx equals to root of ix over the area. So why we want to do something like this? Because this kx, we can call it as radius of gyration. All right, for this area about this x-axis kx. Same goes to ky. Same goes to ky. You can express this as integration over the area, sorry, integration, root of the integration of y with so y, right? I y over the area. Sorry for the noise, the disturbance. Okay, and so as the name suggests, the radius of gyration. So radius, it has a unit of length, right? So what does it imply actually? I mean, you can remember this formula and use them, but what does it imply? It implies the how much this area is spreaded from that exists. You understand that? For instance, the first one, okay, let's take the second one. Okay, this area, right? This area A, how much this is spreaded from the y-axis, right? Because you know the IY, you have calculated IY, so you know you want to find how much actually this spread, how much this distance from this is the far away. Okay, and this characteristic is important when you want to design columns in such mechanism. In particular, all right, this rate of gyration, you may want to use this when you want to design columns. Okay, columns is something like, just a side note. Okay, column is something like this. You have a cross section and it's a prismatic, and then you have a line of that, right? And then you apply the load, right? And then you have support, for instance. Of course, the other side will have traction, right? So you might need to know for this cross section what is this R. Okay, okay, let's use K, radius of gyration. Okay, because we want to design this column, there is a relation between this radius of gyration with the length, right? If if it is too slender, then it is quite dangerous actually for this column. I mean, that's another thing. Probably you will find in mechanics of materials or structural mechanics, right? But this is the application of radius of gyration. Okay, so this is example, still the same example, F10.1. Okay, but here this example 10.1, you want to use 10.2 parallelization theorem to solve this, right? So that's why here, though you want to find Ix, right? You want to find Ix, but now you do not draw vertical dA. You want to draw the vertical. Okay, so here you draw vertical, though you want to find Ix, right? And then use this one, right? And then use the parallel axis theorem, and then you solve that. So you have to check this, right? And this is the same. You want to find moment of inertia about y-axis, which is Iy. Okay. If you do 10.1, which is the direct integration, you need to draw, because it's Iy, so you need to draw a differential element which is parallel to y-axis, right? And that's what we did for F10.4, right? But here you want to use parallel theorem, so you draw this differential element which is parallel to x not y, right? Like this. Then use the parallelism theorem, and then you will get the same answer. All right. Again, remember in 10.1 you cannot draw like this. I mean, if you want to find Iy, you have to draw something differential which is perpendicular to y, not x, right? But again, I said actually you can do that, but you need to do parallelism theorem in 10.2. Okay. Okay, this is the last part, which is 10.4, moment of inertia for composite areas. Okay, we have discussed about composite area, consists of series of connected simpler parts or shapes, right? Like a rectangle or rectangle, square, circle, semicircle, right? Quarter circle in your example, right? You have one example of the quarter circle. So the moment of inertia of your convex area will be simply the algebraic sum of the inertia of all its parts, right? You have done the same thing in chapter 9 in the when you want to find the centroid, right? You can, or center of mass or center of volume, right? Or center of length. You can this for the composite areas. You can just simply find the algebraic sum, right? You draw the table. You remember that you draw a table. You put those summation of not summation the area the area the centroid area, right? X y x still there, y still there, z still there. So now in this 10.4 you will do the same thing, but not for the centroid but for the moment of inertia if you have the composite areas, right? So the procedure, the first one for the composite parts, you divide into the parts, right? And you indicate the centroid, okay, of each part to the reference axis, okay. And then you do the Paresis theorem. Do you know why? Because it's a composite area, right? For instance, you have this, this, and this. Can you see that you have three parts? For it, of course, do all this. For instance, the centroid for the middle one is here. The centroid for the top one is here. Something like that, right? Centroid for the bottom one is here. So they do not share the same central axis. This one, and this one. So that's why you need to use the parallel axis theorem 10.2 that you have just learned. Alright? Okay, this is more explanation on the parallel axis theorem, why we want to do that and when we want to do that, okay, to use the parallel axis theorem. And you do the summation. Okay, so you use summation. Here again, you can use you can define minus as well. You remember we have minus area, right? Here you can have minus what call it, the moment of inertia as well if you want. Okay, just a quick note on this. Basically, in chapter 9, you have seen the centroid, location of the centroid for these shapes, right? But here, in this table, you can call it table, the moment of inertia for these, they are defined. Okay. For instance, if it is a rectangle with base B and height h, okay, base B and height h, the moment of inertia about the is own centroidal x-axis, x prime, it is 1 over 12 b h cubic. Okay, this formula. Same goes to this one. For I, for y, it is 1 over 12 h b cubic. All right, basically it means that the 1 over 12 times the length which is parallel to that axis times the length that is perpendicular to that axis. Okay, cubic. That's what it means. All right, so you have this, and for triangle it is 1 over 36 dh cubic. Okay, for circle it is like this, 1 over 4 pi r squared. Sorry, pi r 4 over 4. Okay, and because of that, so the j, the potential is 1 over 2 pi r squared, pi r power 4, okay, not squared, power 4. Okay, and semicircle again, you have this formula. For the quadricycle, you have this formula, and for the ellipse, you have this formula. All right. Why do you want to look at this formula? Actually, you can try to derive the formula by using 10.1 and 10.2. Okay, you can do that, but this is simpler shapes. So more most of the time for composite areas, actually you have these simple shapes. You can have the rectangle, you can have triangle, okay, mostly, or you can have semicircle, for instance, quarter circle, okay. So that's why mostly it is rectangle, okay. Let me tell you, okay. Mostly, I mean, most of the design, not most of the question, okay. Most of the design will be about rectangle, okay, simple rectangles. So 1 over 12 BH to be is quite important, right? This is the example. You have this cross shape, the beam with the T or cross section, right? So the question asks you to find moment of inertia of this beam, which is composite, right? Can you see that? This is a composite about centroidal x and y axis, which is I x and I y, and your x is this, your y is this, both of them passing through its centroid. Okay, so you were told actually the centroid is here at the origin, right? And you have the dimensions. Yeah. So how many sections, how many parts that you want to make out of this? You can do 1, 2, 3, 4, 5. You can do 5 if you want, and you can do 3 as well. So that's up to you to choose, right? How much do you want? You can, in this example, actually gives you this for this first one, right? This is the first segment. This is the second segment. Sorry, it's not straight. This is the third segment. It's okay. You see that? This is the first. This is the second, and this is the third segment. It's okay. So again, you do the table. You make the table. Segment 1, segment 2, segment 3, right? And then you find the areas individually. Segment 1 is 200 plus 50 plus 200, which is 450, times this length, which is 50, right? Same goes to the area for 2 and 3, right? And then you find this Ix prime, Ix bar, which is the mode of inertia about its own x-axis, right? Its own axis. For instance, this one is, they share the same axis, okay? And then that's why, because all of them, they share the same x-axis, they have the same x-axis with their own x centroid axis is the same as the x-axis, global axis. So that's why their dy squared, dy are zeros, right? Which means that you don't have to use the parallaxis theorem for Ix, right? Okay, and then if you multiply with a dy squared, it will be zeros as well, right? Because the dy's are zeros. But how about the iy? Okay, this is the thing. If you check, if you really look at it, for segment 1, the iy is own y will be the same y. I mean, it's like this. This is number 1. This is y-axis, right? This y-axis, and its own y prime axis is the same axis. This is okay. That's why when you calculate it, it will be like this: 1 over 12 h cubic, right? And the dx is 0, right? Same like the previous ix. Okay, you don't have to use the parallaxis theorem. Okay. But what happened to number 2 and number 3? So again, this is y-axis, isn't it? Number 2 is something like this. Allah, it's not. Let me try to how to cancel, erase. Let me erase this. Okay. Erase, erase. Okay. Pointer again. Pen. This is y-axis. Okay. So number 2, segment number 2 is like this, right? So where is this? Where is its own y prime axis? Centroid is here. Okay, in the middle, right? In the middle of 150. So the centroid is here in the middle. So this is your y prime axis. Do you understand that? So when you want to find I, y bar, you find about this axis. 1 over 12, this is the base, and this is the height, cubic. Is it okay? But now you have this distance, right? This distance from the y-axis to its own y prime axis. Okay? You use the parallel axis theorem. Okay? So this is your dx. Okay, that's why you have dx here. Okay, this is your dx minus 100, and you square it becomes 10,000, right? And then for the segment number 3, for segment number 3, again you have this is y prime axis passing through its centroid, right? And then you have this dx, and this dx is 100 plus 100 because because of relation, but when you square that one will be same. Okay, and then you multiply this dx squared with the a, you get this. Okay, and then you sum them up. Okay, why you want to do that? Because of this formula. Okay, so if you want to find ix, it will be this summation, right? And you want to find iy, then you need to be careful because you have this and you have to plus with a dx squared, right? Okay, so this is iy prime, and this is a dx squared. Okay, in ix you just have I x bar because all of them they have the centroid at the x-axis, the real x-axis. Okay, is okay. So these are your moment of inertia about x-axis ix, moment of inertia about y-axis iy for this composite areas. All right, and this is another example. Some of these inshallah we'll discuss in the tutorial solved on the whiteboard. I hope be coming soon, inshallah. Okay, and for this area, actually, you can use, or actually here, the segment number 2 is a negative area, segment number 2. So you subtract and see this subtract. Like what we did for the whole. Chapter 9, example with whole, right? Okay, 10.7, another example. So, an example, okay. So this is the end of chapter 9. Sorry, chapter 10, word of inertia. Uh, inshallah, the rest of the tutorial will be posted soon, inshallah. Okay. Thank you for listening. Assalamualaikum.